The Saturn Conspiracy. Why NASA buried Cassini's final image, ancient alien defense system. The rings weren't supposed to make noise. Yet in Cassini's final 19 seconds, a pulse rose from the static, steady, deliberate, sync to Saturn's heartbeat. Then the transmission died. Hours later, a junior analyst stared at 27 misfit pixels in a wide-angle frame and froze. They formed a lattice no storm could sculpt. The file vanished from public servers within days. To understand why a dead spacecraft might have brushed an active perimeter, we have to rewind. Back before Cassini dove through the gap. Before an anonymous backyard astronomer posted a silver disk holding position by the rings and refused to explain itself. Rewind, first glimpses and early doubt. 400 years earlier, a different set of eyes blinked at something that didn't fit. Galileo called them ears, awkward handles on a golden world. His lenses were small, the atmosphere was shaky, and Saturn refused to sit still. He didn't see rings. He saw a mystery that came and went, like a warning without words. It was enough to bother him. That discomfort would outlive him. Centuries later, bigger glass and better math gave the rings a name, a thickness, an orbit, a composition. Ice mostly. Dust. Boulders. A system so thin it could disappear edge-on, so broad it could swallow a million stories. It was elegant. It made sense. Until it didn't. Get this, Voyager flew by and found the spokes. Shadowy streaks sliding across the rings, dark from above, bright from below, appearing in seasons like a clock set to a calendar we didn't write. Spokes shouldn't hover, they did. The explanation bent toward charged dust and magnetism, a workable sketch, not a full answer. The hexagon at the pole showed up too, crisp and stubborn, a six-sided jet stream that refused to drift into chaos. If you were hunting a pattern that felt engineered, those were the first crumbs. But scientists live by a rule: weird is allowed. Weird is often natural. So the story held. Rings formed late, maybe from a lost moon shredded near the Roche limit. The age estimate, 2 to 400 million years, fit some models, annoyed others. Meanwhile, another detail slipped in around the edges. The rings were raining away, bleeding an Olympic pool of water every half hour into Saturn's upper atmosphere. You could watch a marvel evaporate on geological time. Beautiful, grim, natural. Then a man in a backyard pointed his telescope at Saturn and ran thousands of frames through a stacking app. He expected turbulence, a softened edge, the usual. Instead, a silver disk sat just off the rings and refused to budge. Frame after frame, same spot. Not a satellite, not a passing glint. He checked the ROS, the disk stayed. He posted the result quietly, almost apologetic, and waited for someone to explain it away. Some tried. Artifact. Reflection. Dust. But the position consistency broke those theories. If it moved, stacking would smear it. It didn't move. It held like it belonged there. A few seasoned imagers compared their sessions from similar nights and saw nothing. That didn't help. It made the disk either a one-off or an appointment someone else missed. Meanwhile, something else was happening far from that backyard. Cassini, deep into its mission, threaded the needle between planet and ring, sampling dust, tasting fields, mapping gravity. Each pass said the gap was survivable, barely. You could call it a rehearsal for a last act nobody wanted to perform. The directive was simple. Learn everything, then die where no microbe could hitch a ride to Enceladus or Titan. A clean end. In those final days, Cassini took a wide-angle shot near the South Pole. Unremarkable at first glance. Atmospheric bands, subdued light, the giant being itself. That image sat in an archive until an AI trained on structural anomalies saw 27 pixels that didn't match turbulence. The machine teased out symmetry and built a three-dimensional lattice hovering above cloud tops, aligned to frequencies Cassini had logged as noise. Not a storm, not compression error, a configuration with intent. Before anyone could argue in public, the file trail thinned. Mentions disappeared. The team working the anomaly went quiet. If you're used to open data, that silence rings louder than a press release. And yet no one said debunked. They just moved the conversation into rooms without windows. Back to the human side, the amateur who posted the disk kept his tone careful. He wasn't claiming alien anything. He said what he saw, a smooth, reflective object, metallic in its behavior, casting no shadow on the rings, steady through thousands of frames. The consistency mattered. It said, "I'm here by choice." Or it said, "Your method pinned me to your view." Either way, it resisted the usual list. What nobody knew at the time was how these threads would tangle. The spokes returning seasonally like deliberate sweeps across a minefield. The hexagon's persistence hinting at a stabilizing geometry. The ring rain acting like a slow fuse. The silver disk sitting on station. The final Cassini pulse locked to the magnetosphere, as if syncing permissions before a door opened. While that was happening in Pasadena, on a forum in the wrong time zone, a user mirrored the amateur's image and drew a clean circle where the disk sat. Behind the circle, faint striations in the ring texture curved slightly out of alignment with known dynamics. It could have been noise, or it could have been a seam, a join. One detail would matter later. The disk sat near a region where spokes tended to nucleate. This was the moment everything changed, not with proof, but with the suspicion that we were asking the wrong question. Not what is the anomaly, but what job is it doing? If you're defending a world too soft to hold a wall, you don't build towers. You build distance. You control the approach. You make a ring look like ice. To understand how a perimeter can hide in brightness, we need to follow the people who kept looking when the files went dark, and trace the first time the rings pushed back. Voyager's shock, edges too sharp. 3 days earlier, something strange occurred in a cramped control room crowded with coffee cups and dot matrix printouts. A technician zoomed in on a fresh Voyager frame and frowned. The A-ring's boundary looked wrong, not messy and feathered like nature prefers, but knife clean. There was a line where chaos should have frayed. He didn't say impossible. He said, run that again. Stakes first. If the rings are a debris field, their edges should blur under constant jostling. Gravity tugs, moonlets stir, micrometeoroids sandblast. Over time, the rim should look like the hem of an old shirt, threads everywhere. Instead, the data showed an edge you could cut your thumb on. What's at risk? Our model of how rings live and die. And for the people in that room, reputations. You don't publish sharp edges without a fight. Action. Voyager's cameras scanned across the ring plane, and analysts measured brightness gradients pixel by pixel. The transition from bright ring to darkness wasn't a gentle slope. It dropped like a cliff over a distance too short to reconcile with predicted particle diffusion. Meanwhile, wave patterns, bending waves from moons, density waves from resonances, behaved as expected in some sectors and then abruptly stopped, as if they'd hit a boundary condition no equation had included. One engineer circled a zone and wrote, "Why doesn't this bleed?" Unknown to them, across town, a theorist ran collisional dynamics on a mainframe and tried to dial in a parameter that would keep edges tight without a hidden hand. Increase self-gravity clumping? The edge softened. Reduce particle size dispersion? It softened again. Introduce shepherd moons? Yes, Prometheus and Pandora do carve sharp lanes around the F-ring, but the A-ring's outer edge looked even meaner than the shepherding could justify. He pushed a note uphill. We're missing a constraint. Impact. Papers came, cautiously framed. Unusually abrupt transitions. Shepherding insufficient. In the margins, private admissions, it looks engineered. Nobody wrote that. They wrote, unexpected coherence. The ripple effects were subtle but real. Instrument teams started asking for higher resolution scans of edge regions. Grant proposals grew bolder. Investigate non-gravitational processes, plasma interactions, embedded fields. You could feel the field inch toward a heresy without naming it. Meanwhile, something else was happening inside the images, microstories hidden in the grain. A junior analyst noticed a faint scalloping pattern repeating along one rim, a periodicity too regular to be random noise. When mapped against orbital resonances, it didn't line up cleanly. It lined up almost, then slipped like a lock that required the right key. She flagged it, caught a shrug, and kept the printout under her notebook. Years later, Cassini would see similar scallops. By then, the language had softened, edge modes. Still, the first glance mattered. It felt too tidy. Here's where it gets uncomfortable. Saturn's magnetic field threads the rings. Charged dust couples to it. That's the orthodox route to explain the spokes and some transient features. But magnetic pressure doesn't draw straight lines on kilometer scales, not without structure. In Voyager's radio science data, the refractive index changes at the edge behaved as if the particles weren't just thinning, they were aligning. Alignment implies preference. Preference implies a rule. Whose? Stakes again. If an unknown rule governs the boundary, then our safe assumption, rings as passive victims of gravity and chance, fails. And if the boundary is more than a line, if it's a surface with properties, then anything crossing it would feel something. drag, charge, a nudge, a warning. Future missions, even hypothetical crewed flybys centuries from now, would have to rethink approach vectors. The cost isn't just academic, it's navigational. Action widened. Teams compared Saturn's edges to those of Uranus and Jupiter. Jupiter's rings are dusty veils. Uranus's are narrow and surprisingly sharp, often cited as ring systems that demand shepherds and strange physics. The comparison did not comfort anyone hoping for a tidy Saturn story. Instead, it hinted at a class of solutions that kept cropping up: active maintenance. In nature, maintenance usually means feedback. Ice sublimates, charges, recondenses, repeats. But feedback without a driven rhythm meanders. The edges Voyager saw moved, yes, but they moved like taut lines under tension, snapping back from perturbations faster than models liked. Impact cascaded into mission planning. Decades later, Cassini's ring-grazing orbits were designed with these edges in mind. Instrument modes shifted to capture boundary behavior. Radio occultations slicing through the rims, stellar occultations measuring particle size spectra across the drop-off. The results kept whispering the same thing. The transition wasn't just a change in number, it was a change in state. Particles just inside the edge acted differently than their neighbors a few kilometers inward, as if they'd been sorted, sifted by an unseen sieve. They didn't know, back in the Voyager days, that a pulse would ride Cassini's final breath. They didn't know an amateur would catch a disk hanging near the ring's calmest brink. But they had this: edges too sharp, coherence too stubborn, a perimeter that behaved like it cared about being a perimeter. This was the moment everything changed, because the question, how did the edge get sharp, became who keeps it sharp. Not with certainty, nobody could claim that, but with a nagging suspicion that the rings weren't just scenery. They were a boundary, and boundaries are usually built for a reason. Cassini moves in, the data that wouldn't behave. While that edge question simmered, Cassini arrived with the patience Voyager never had: years to circle, sample, and press on the seam. Stakes first. If the edges and spokes hinted at a boundary with rules, Cassini could test those rules. Get too close, and you'd learn whether the boundary pushed back. Stay far, and you'd learn nothing new. The mission split the difference, then crept inward. Action. Early ring-grazing orbits ran stellar occultations, starlight flickering through ring particles like a barcode. The pattern should have smoothed with distance. Instead, fine-scale structure persisted stubbornly, repeating at intervals that didn't line up with known resonances. Meanwhile, radio occultations measured refractive shifts that jumped, not drifted, when crossing certain lanes. An instrument lead said softly in a review, "We're stepping across thresholds." He didn't mean philosophy. He meant physics. Meanwhile, something else was happening at the pole. The hexagon refused to blur, but Cassini's thermal maps showed temperature gradients snapping into place faster than expected after seasonal shifts. Weather changes should smear energy. This pattern locked in, as if a mesh guided the flow. Teams tied it to jet dynamics powered from depth. Reasonable, but the speed bothered people who'd shepherded models for decades. It looked like a system that liked returning to a template. Back in the rings, the spoke season returned. Cassini's cameras caught ghostly streaks blooming and fading across the B ring, dark from above, bright from below. Charged dust riding magnetic field lines, textbook. But a timing quirk gnawed at the radio team. A low-frequency hiss, usually blamed on plasma turbulence, shifted into a rhythm, subtle, repeating, near the onset of spokes. It wasn't musical. It was mechanical in the way a lighthouse is mechanical: swing, pulse, swing. In internal notes, someone wrote, "gating," and circled timestamps. Impact. Operations adjusted. On subsequent passes, they synchronized radio modes to the onset window and saw the hiss split. Two frequencies, beating against each other, one tied to Saturn's magnetosphere, the other drifting with the ring's local frame. Where they crossed, spokes emerged more often. A coincidence? Maybe. But in the room, you heard chair legs scrape a little slower. Cassini pushed closer. Dust counter readings, expected to spike randomly, spiked in precise bands, then went quiet, then spiked again like lanes of traffic. Particle size distributions tightened near certain edges, as if something sorted the small from the slightly less small. Models could coerce similar effects via seasonal charging, but not with that crisp repetition. A postdoc overlaid the dust spikes with the radio beat map and went pale. They lined up more often than chance would like. He didn't call it proof. He called it alignment pressure. Unknown to them, across the hallway, Magnetometer data mapped an oddity. Localized kinks in field lines threading through the main ring's stable over. Multiple orbits, shifting only with Saturn's slow wobble. The field should have smoothed, instead it scalloped. The simplest read was frozen in flux tubes tied to conductivity variations in the ring plane. The more provocative read was embedded structure, conductive elements channeling charge. Out loud, they said the former. In private, some considered the latter. Nobody wanted to be the person who said wires. Meanwhile, the grand finale loomed. 22 dives between the innermost ring and the cloud tops, the region nobody had touched. Stakes surged. If there was a boundary with bite, Cassini was about to feel its teeth. On the first plunge, dust counts baffled, lower than feared, higher than comfortable, with bursts in tight clusters. The plasma wave instrument recorded crackles that walked right up to the magnetospheric beat, and then stepped off in lockstep, like a runner merging onto a track. An engineer muttered, "We're being handed off," and then pretended he hadn't said it. Data kept refusing to behave. Gravitational field solutions, extracted from Doppler shifts as Cassini swooped, showed mass distributions under the rings that didn't match the visible density alone. It was subtle, within error bars if you were generous. If you weren't, you noticed pockets of extra pull that tracked with long-lived ring features. Explanations sprawled, moonlet wakes, self-gravity wakes, layered clumping. All valid. Yet the persistence across seasons scraped at the edges of those models. It looked curated. Human reactions mattered. In debriefs, you heard the language soften into hedges. Coherent, persistent, phase-coupled. You also heard defense. One PI said, "Nature is better at building order than we give it credit." True. Another replied, "Order likes energy." Also true. The room paused there, because energy implies a source, and a source implies power moving with purpose, or at least with a feedback that doesn't drift. Impact radiated beyond papers. Trajectory planners penciled warnings into hypothetical future mission profiles. Avoid crossing boundary regions during high-charge seasons. Expect unmodeled torques near specific longitudes. Anticipate radio interference synchronized to planetary rotation. It wasn't fear. It was respect for the unknown. Then came the last days, the dives that would end in heat. The final 19 seconds added the pulse the opening already stole, a rhythm tucked under the noise, sinking to the magnetosphere, aligning to a geometry nobody had licensed. At almost the same moment, a wide-angle frame registered the misfit pixels near the south, the lattice suggestion the AI would later surface. In the control room, nobody saw a lattice. They saw a green trace flatten and a clock run out. What nobody knew at the time was how neatly the pieces would stack. Sharp edges that acted like thresholds, spokes gated by beats, dust lanes that felt scheduled, field lines that kinked where maps drew clean curves, gravity tugging from where brightness alone couldn't account for it. A pulse at the end, as if something acknowledged the crossing and marked it. This was the moment everything changed, because Cassini didn't just catalog a ring system. It mapped a behavior, and behavior suggests an actor, or at least a design. If the rings were passive, the data should have smeared into averages. Instead, it snapped into patterns. The perimeter wasn't quiet. It was active, and we had brushed it. Enceladus, a moon that acts like a machine. While Cassini was mapping behaviors in the rings, something smaller kept interrupting the narrative with physics that felt procedural. Enceladus, an ice world the size of Arizona, should have been quiet. Instead, it pulsed. Vents at the South Pole opened and closed like valves, firing plumes hundreds of kilometers high. If you were designing a system to seed, to shield, or to signal, you'd use a metronome. Enceladus had won. Stakes first. If those plumes were random, they'd tell a story about heat and fractures. If they were scheduled, they'd suggest control, tidal sure but tuned. What's at risk here isn't just how we draw Enceladus on a slide. It's whether we admit that a moon can function like a subsystem of a larger architecture, exchanging material and charge with the rings as if following a plan. Action. Cassini flew through the jets and tasted ocean, water, salts, silica, organics. That alone rewrote textbooks. But the timing mattered. The strongest plumes rose when Enceladus sat at a particular point in its orbit, near epicenter, when tidal flexing should be maximal. Textbook again. Except the cracks, the tiger stripes, didn't just breathe with tides, they fluttered with smaller rhythms, phase-locked to Saturn's magnetospheric rotation. The magnetometer picked up minute modulations riding the larger tide. A plume isn't supposed to care about magnetic beat. This one twitched to it. Meanwhile, something else was happening in the E-ring, the vast, diffuse halo sourced by those very jets. Particle sizes varied with distance as expected, but their charge states grouped, repeating in bands that mirrored Enceladus's orbital cadence. On certain passes, Cassini's dust analyzer recorded bursts of specific grain sizes with almost metronomic spacing, the kind of packetization you'd expect if a valve were strobed. A postdoc joked, "Who's clocking the geyser?" Nobody laughed long. The histogram looked too neat. Human reactions revealed the divide. Geophysicists leaned on tidal heating models, pockets of melt, controlled by pressure and fractures, modulated by orbital mechanics. Strong, elegant. Plasma folks pushed back with data. The plume electrons didn't just fluctuate. They gated, opening windows of enhanced conductivity when Saturn's magnetic longitude rolled past certain values. That gating aligned suspiciously well with spoke-onset windows in the rings. Two widely separated phenomena, dancing to a shared rhythm. Impact. Map Enceladus's output against ring rain signatures in Saturn's atmosphere, and an odd correlation appears. On weeks when plume intensity jumped, ultraviolet signatures of ring-derived water at mid-latitudes brightened slightly earlier than transport models liked. It was a sniff, not a meal, subtle, arguable. But to the team stitching behaviors together, it looked like the system talking to itself. Moon vents, ring charge, atmospheric glow. 3 notes in one phrase. Now, if you're building a perimeter that has to maintain brightness, absorb impacts, and police approach vectors, you need a reservoir and a sprayer. Enceladus is both. Its ocean is the reservoir. Its south pole is the sprayer. The E-ring becomes the fog that fills the gaps, replenishes fines, restores reflectivity, and carries charge. Seasonal tilt changes the load. The sprayer adjusts. That's the story the data tempts you to tell. Not a conspiracy, an operating manual. But there was one problem. Energy. The numbers were brutal. Keeping Enceladus this active for millions of years strains tidal budgets. Models patch it with episodic bursts, orbital resonances, and crack self-regulation. Plausible, yes. Yet Cassini caught Enceladus in sustained output over a decade with a consistency that felt more like a thermostat than a volcano. Get this, thermal maps of the Tiger stripes showed hot spots holding temperatures through orbit phases when cooling should have bitten harder. Not flat, but flatter than passive response. Microstories kept adding texture. On one fly-through, Cassini's radio system took a whisper of interference at a frequency that, when beat against the magnetospheric pulse, matched a subharmonic recorded during spoke formation hours later. The team didn't publish a line between those points. They underlined both and wrote coincidence. The coincidence kept visiting. Meanwhile, the surface around the vents behaved like engineered skin. Fresh snow fell from the plumes, but it didn't pile randomly. Grain sizes drifted into patterns that steered heat loss along the stripes, keeping vents unclogged. Self-organization can do that. Feedback between deposition and sublimation writes beautiful patterns in nature. But standing on the data, you felt a nudge. This system likes staying open. Impact rippled to the rings. Regions downstream of Enceladus's orbital path showed subtle tightening of particle size distributions after high-output weeks, as if the fog laid down a calibration layer. Optical depth curves in those sectors smoothed. Radio occultations saw refractive jumps sharpen, then relax. Maintenance cycles? The word hovered in the back of minds. And then the human moment. A grad student compared the timestamps of Enceladus's brightest plumes with the amateur's silver disk session. No overlap. Different nights, different geometry. Irrelevant? Maybe. But on one of the disk-free nights, a spoke train ran hot near the region where spokes often nucleate. On an Enceladus-busy night, spokes hesitated, then surged as Saturn's magnetic longitude rolled past a familiar sector. To her, it suggested shared scheduling, not controlled by Enceladus alone, but participation in a choreography. Here's the point. Whether you believe in an ancient defense system or a ruthless, self-stabilizing natural machine, Enceladus behaves like a service module. It feeds the ring, tunes the charge, and listens to a clock that isn't only its own. If the rings are a perimeter, Enceladus is the pump. If the rings are ice and sunlight, Enceladus is still the pump. Either way, you can't explain the boundary without the valve that keeps it alive. The defense hypothesis, if rings are a shield. Now remember, none of this proves intent. But if you treat the rings as a system built to do a job, the pieces start clicking in ways our models struggle to. So what job? The simplest defensive role isn't lasers or walls. It's distance, drag, and denial. A planetary scale keep-out zone. Start with distance. A ring that looks fragile is actually vast. Any inbound object, a rock, a probe, a ship in some future, has to cross a gauntlet of particles moving at orbital speeds. At first glance, random collisions. But if the edge behaves like a threshold, then the outer lanes become more than scenery. They're the first layer of a filter. Large intruders get shredded into fines. Fines become charge carriers, charge couples to the field. The perimeter turns mass into signal. Drag is the second job. Those spoke seasons we saw, charged dust levitating, then settling, don't just make pretty streaks. They're windows of enhanced coupling between ring particles and Saturn's magnetosphere. In a defense frame, that's the system turning up its stickiness. Anything crossing during a high coupling interval would feel a fog that grabs electrons, builds surface charge, and forces it to dance to the planet's beat. Navigation goes from smooth to syrup. Precision becomes guesswork. That alone can deny approach without firing a shot. Denial works best when you can modulate it. That's where the rhythms matter. The spoke onset tied to a magnetospheric pulse, the dust bursts in lanes, the kinks in field lines that stay put. All that looks like a switchboard. If you can predict the beat, you can open and close pathways, create corridors or close them, steer charge toward an intruder's hull at the worst possible moment. We say natural gating in papers. In a manual, it reads, variable impedance barrier. Meanwhile, something else was happening in the atmosphere, ring rain. Water, ice, and organics falling along field lines, heating bands, shifting conductivity at specific latitudes. In a natural story, it's a sad leak. In a defense hypothesis, it's a replenishment and calibration loop. The fall adjusts the planet's ionosphere, just enough to tune how the magnetosphere couples back to the rings. Feedback. You get a perimeter that can stiffen or relax, sharpen edges, or blur them, depending on the clock and the threat. But there was one problem. Power. Where does the energy come from to keep a perimeter responsive for millions of years? Here's the pragmatic answer. Saturn supplies it. Rotation, tides, sunlight, impacts, all feed a giant battery. The rings don't generate so much as they rectify en route. Think of a coastal breakwater that harvests wave energy, then moves it where needed. The hexagon's eerie stability fits here too. It's not a turret, it's a flywheel, a deep atmospheric mode that stores and releases momentum, helping lock the planet's magnetic rhythm that the rings then ride. What about the sharp edges? In the defense frame, they're not just boundaries, they're phase boundaries. Surfaces where particle size, charge state, and orbital alignment snap into a preferred configuration. Cross that surface and local rules change. Your hull sees different charging. Your sensors saturate on a beat you can't filter without losing guidance. Your trajectory picks up tiny torques that add up over minutes. You don't get torn apart theatrically. You get confused, delayed, scraped, and finally bled into dust. Enceladus re-enters as logistics. A shield needs supply. The E-ring's finds are the consumables, optical brighteners, charge carriers, sacrificial grains that take the hits and keep scattering light to mask anything embedded. The jets act like timed injectors, pulsing more during seasons when ring charge wants to sag, less when sunlight can shoulder the load. If a perimeter must recover quickly after a meteoroid storm, you turn the sprayer up. Cassini saw that consistency. It looked like a thermostat because in effect it was. Then the human factor, the silver disk. In a natural read, it's noise or a rare alignment. In the defense read, it's a service node, a calibration target, a beacon sitting near a spoke nucleation region, holding position where edge rules are strongest. It casts no shadow because you're not meant to track it optically, you're meant to feel it electromagnetically. If Cassini's late pulse was acknowledgement, the disk is the lighthouse lens, unseen until the fog lights. Get this, the hypothesis doesn't require aliens hovering today. It allows for an ancient construct that leverages planetary physics, so well it looks alive without constant hands-on control. A self-healing barrier whose default state is beautiful, whose function is unfriendly to precision. Over eons, parts fail, parts persist. The natural machine we describe is the camouflage. The operating principles are the payload. What nobody knew at the time was how often defense looks like maintenance. Keep edges sharp. Keep beats steady. Keep intruders busy. Even if you hate the word artificial, you can admit the system behaves like a purpose-built filter. And if that's true, the quiet warning in Cassini's last 19 seconds isn't spooky. It's procedural. You touched the threshold. The threshold answered. Myths, omens, and the hexagon. Before engineers wrote code for ring occultations, storytellers were already trying to name what Saturn does to the human mind. In Rome, the god Saturn devoured his children to keep his throne. In agriculture, he ruled the sowing and the sickle. In astrology, Saturn still means boundary, limit, time's edge, the planet that says no. You can laugh at horoscopes and still notice the echo, a world defined by rings that function like a line you don't cross. Meanwhile, something else was happening in the north, a storm that looks like a symbol. That hexagon, 20,000 miles across, crisp as a stamp, sits over the pole like a geometric omen, changing color with the seasons but not its shape. We've said it's a jet stream stabilized by deep convection, and that's good physics. But the human brain can't help tagging a six-sided cyclone as a sign, because signs are what hexagons do in the rest of our life. They tell us to stop. They mark hives, cells, lattices, instructions. Stakes first. If a culture thousands of years ago looked up and saw a harvest god with a scythe and a dour temperament, and we, with spectrometers, see a planet that enforces boundaries through rhythm and drag, the overlap isn't proof, it's resonance. What's at risk is our willingness to learn from the way myth files the world, by function. Saturn, the limiter. Saturn, the keeper of time. In our data, the magnetospheric beat that gates spokes is literally a clock. The hexagon locks phase with winds from deeper levels, storing and releasing momentum with eerie patience. That's timekeeping in gas. Action. Cassini watched the hexagon wake from winter darkness and snap back into form faster than modelers expected. Thermal gradients fell into place like tiles. Spiral waves in the eye rotated like the hand of a slow clock. Color shifted from blue to honey as haze chemistry rebalanced, yet the edges stayed ruler straight. In parallel, ring spokes returned with seasonal sunlight, and low-frequency pulses in the radio bands found their stride again. Two very different phenomena, both settling into recurring patterns that felt less like weather and more like a schedule. Micro-stories surfaced. A radio engineer, raised by a grandmother who read ephemerides at the kitchen table, stared at the phased pulses and murmured, "Saturn keeps appointments." She didn't mean fate. She meant there's a cadence that other processes meet. In a separate office, a historian dug up Babylonian tablets that tracked Saturn, Ninib, over decades, noting its slow, implacable march. The texts had no hexagon, of course, but they gave Saturn the job of enforcer. Even without physics, they felt the perimeter. But there was one problem. Symbols seduce. You can smuggle intent into a hexagon because our eyes crave meaning. So we tested the meaning with numbers. Teams mapped the hexagon's wave number against wind profiles across altitudes and found a band of stability that shouldn't exist without deep forcing. The jet behaves like a waveguide. In the defense frame, that's a transmission line, an energy reservoir that helps keep the magnetospheric rhythm steady. In the natural frame, it's still a robust structure that resists entropy better than it should. Either way, it acts like infrastructure. Impact. Once you let the hexagon be more than a pretty storm, the story expands. The polar mode couples to the global field. The field couples to ring charge. Ring charge gates spokes. Spokes modulate drag. Drag enforces a boundary. The chain reads like myth because myth compresses. Saturn says no becomes the hexagon steadies the clock that the rings use to police their edge. Different languages, same job description. Meanwhile, the human need for omens hasn't vanished, it's updated. The amateur's silver disk sat near a spoke nucleation corridor. The last Cassini pulse synced to the planet's beat. People stitched that together with the hexagon's fixed face and heard a warning. Our policy here is simple. Show the data, admit the temptation, separate metaphor from mechanism, and then ask what the metaphor got right. Saturn is a teacher of boundaries. It always has been. Here's where it gets practical. If future probes try to skim those inner paths, mission designers will have to fly by a clock kept, in part, by a six-sided storm. Miss the window, and you meet a stickier fog, a sharper edge, a louder beat in your radios. Hit the window, and the barrier relaxes just enough to let you pass without being shaved into fines. That isn't prophecy. That's procedure learned from a cosmos that's very good at writing rules in shapes we recognize. The hexagon isn't a carved sign. It's a standing wave that behaves like a sign, stabilized by depth and fed by rotation. Myth saw the boundary first. Instruments followed. If the rings are a perimeter, the hexagon is the clock on the gatehouse wall. Structural clues, gaps, waves, and control logic. To see the perimeter's logic, you don't look at the glitter, you watch the gaps. The Cassini division isn't empty, it's patterned. From afar it's a dark moat. Up close it's lanes, wakes, and ripples that behave like traffic under rules. Stakes first. If a ring is just rubble, long-term structure should wash out under collisions. If it holds lanes with repeatable boundaries and wave trains that start and stop on schedule, that's not chaos. That's control. Action. Cassini's stellar occultations turned stars into scanners. As a bright point slipped behind the rings, the signal dimmed and brightened, tracing density with absurd precision. In the Cassini division, density waves spawned at resonances with Mimas and other moons looked textbook, spiral crests, predictable damping. Then something strange, wave packets that began crisp, ran for a few hundred kilometers and quit early, as if encountering a region with higher effective viscosity. Natural? Maybe. But the cutoff distances repeated across longitudes like zones with different rule sets. On maps, they formed belts, not random blotches. Meanwhile, something else was happening along the Bering boundary. Bending waves, vertical undulations, rose and fell with phase coherence across sectors separated by thousands of kilometers. Vertical motions should decohere fast when particle sizes vary. These didn't. They marched like a sheet tugged from below, and their nodes sat suspiciously close to long-lived kinks in magnetometer maps. Team notes use safe words, coupled modes, stiffness anomalies. In the hallway, someone said, "Those look pinned." Microstories surfaced from the F-ring, the notorious chaos strip braided by Prometheus and Pandora. On some passes, Cassini caught streamer channels, narrow incursions carved when Prometheus yanked particles. The surprising part wasn't their formation. It was their healing. Channels refilled faster than collisional models predicted, regaining baseline optical depth in hours, not days, and the refill rates depended on Saturn's magnetic longitude. That's not a moon's gravity. That's ring plasma coupling handing out permission slips. Back in the A-ring, nonlinear density waves stacked into overstable oscillations, self-excited, repeating crests that, in lab disks, arise when viscosity and self-gravity strike a balance. Cassini measured patchwork fields of these microwaves with meter-scale spacing, arranged into grids that drifted but kept spacing ratios eerily constant. Overstability explains stripes. It doesn't explain why some stripes snap to harmonics of the magnetospheric beat. A graduate student overplotted the stripe spacing with the low-frequency radio pulse and found a 3:2 clustering pattern too tidy to ignore. She wrote, "Phase locking?" with a question mark, then erased the mark and kept the word. Gaps told another story. The Keeler and Enki gaps host embedded moons that plow waves in the gap edges. Cassini imaged propellers, disturbances raised by kilometer-scale bodies too small to clear full lanes. Propellers should wander under stochastic kicks. Many did. A subset didn't. Their longitudes drifted seasonally, then snapped back, as if their orbits felt drag that turned on and off with the same gating windows that nurse spokes. That implies a control variable, the ambient charge state, setting a brake on specific sizes. Smaller than this fly, bigger than that stall. A filter. Meanwhile, the radio science team found refractive indices stepping across narrow boundaries like dielectric interfaces, optics language inside a ring plane. Inside Zone A, particles acted like one material, inside Zone B another. The transitions lined up with the abrupt edges that had bothered Voyager. If you're wiring a barrier, you lay down layers with different properties, conductive, resistive, capacitive, to shape fields. The ring seemed to do that with ice grains and dust, grading their sizes and charges into a stacked circuit. There was one problem. Natural gradients can mimic circuits when feedback runs hot. Seasonal sunlight modulates photoelectric charging, meteoroid showers inject fines, moon resonances sculpt density. Stack enough processes and you get layers. True. So we stress-tested the natural logic with time. Over 13 years, layers shifted, but their roles stayed put. The same boundary that snapped waves in 2006 still snapped them in 2016, adjusted for precession. The same gap edges that bled, or held did so on schedule. A messy machine is still a machine. Human reactions reflected a split temperament. One camp celebrated nature's ability to self-organize. Granular media grow bands, plasmas form sheaths, disks breed waves. The other camp kept pointing at the synchrony. Patterns didn't just arise, they aligned to a clock. In a whiteboard session, someone drew a block diagram. Inputs: sunlight, tides, meteoroids. Controller: magnetospheric beat. Actuators: charge state, viscosity, vertical stiffness. Outputs: edge sharpness, wave cutoffs, gap healing. It looked like a control loop because it behaved like one. Impact cut forward to mission design again. If waves quit early in defined belts, those belts could be used, corridors of quiet for a probe to slip through during low coupling windows. Conversely, belts of overstable microwaves would be no-fly zones when the beat peaked. Navigation isn't just rock avoidance, it's noise avoidance. Your gyros and star trackers hate structured flicker. The ring provides plenty. Get this, the control logic doesn't need intelligence in the human sense. It needs a stable clock, energy sources, and materials that respond non-linearly. Saturn supplies all three, yet the elegance nags. Why do the packet lengths repeat? Why do propellers stall in season? Why do dielectric steps sit on the same longitudes Cassini's final pulse nodded to? We can write papers about viscosity, collisional damping, and plasma sheets all day, and we should. But when the outputs line up cleanly with a planetary metronome, you're staring at governance. What nobody knew in the Voyager era is how legible that governance would become under long surveillance. Gaps refill on command. Waves march, then halt at thresholds. Edges act like filters. The ring plane isn't just a junkyard. It's a tuned surface. And tuned surfaces aren't accidents, they're functions. Triggers and threats, when the system activates. If the rings behave like a perimeter, then somewhere there's a tripwire. Not a siren, more like a quiet change in rules that turns a scenic disk into a sticky field. Stakes first. If activation exists, we're not just talking about pretty physics. We're talking about windows when approach becomes harder, measurements get scrambled, and trajectories pick up invisible hands. That matters for probes today, and for anything bold enough to cross the plane tomorrow. Action. Start with the seasons. Spokes don't appear year-round. They flare near equinox when sunlight angles thin and photoelectric charging flips dynamics in the ring plane. Cassini watched the onset window creep in, and with it came that low-frequency hiss settling into a rhythm. On days when the hiss split into its clean beat, spokes blossomed faster and traveled farther before fading. The simplest read: higher charge, longer levitation. The perimeter read: gate open, drag up. Activation, not in lights, but in coupling. Meanwhile, something else was happening in the inner gap during the grand finale dives. Dust counters that had been politely noisy turned orderly erratic. Bursts in tight packets, quiet in between, synchronized to the magnetospheric longitude Cassini happened to cross. On 2 passes, the packets sharpened as the spacecraft's ground track approached longitudes tied to stubborn field kinks. Radio noise rose on cue, then fell away like a curtain. You could shrug and say coincidence. Or you could say the curtain lifts and drops on schedule. Threats don't announce themselves as monsters, they announce as frictions. During those same passes, the spacecraft recorded tiny, unmodeled torques. Course corrections so small they lived in the error bars, yet repeated enough to be unnerving. Engineers hate patterns and errors. The torques clustered near ring plane longitudes where earlier occultations had mapped sudden refractive steps. Cross a dielectric-like boundary, pick up charge differentially, feel a nudge. It didn't shove Cassini off path. It breathed on it. That's a perimeter flex. Microstories kept stacking. A star tracker saw momentary scintillation spikes, brief blindness, while peering across the Beering rim at times that lined up with spoke trains. It wasn't a failure, it was a saturation. The visual field filled with structured flicker, overwhelming centroiding for a handful of frames. Guidance recovered, but for those frames, the ring turned sensor truth into snow. If you're flying through, those are the instants when your autopilot trusts ghosts. Triggers can be external too. Meteoroid streams raking the rings inject fines and charge, and Cassini's UV spectrograph saw the planet's mid-latitude glow brighten days later. On some of those weeks, spokes arrived early and stayed late, and the dust counters in certain lanes read richer by a narrow margin. A natural chain, impact finds charge spokes. A perimeter chain, disturbance detected, viscosity tuned, drag raised. The difference is intent. The behavior is the same. Then there's the silver disk. The amateur's stacked frames showed it sitting near a corridor where spokes often initiate. If it's a service node, it doesn't have to move to act. It can bias a local field seed charge or serve as a reference for phasing on nights when similar longitudes rotated. Under sunlight, other imagers saw nothing. That could mean the node only matters when the beat says so. A lighthouse that's dark until the fog rolls in. Meanwhile, the hexagon's clock kept time. As northern sunlight returned, the jet snapped into its six-sided groove and low-frequency emissions stabilized. Weeks later, spokes found their stride. The timing wasn't perfect, nature rarely is, but the order, clock, beat, gate, repeated enough to feel like a sequence. If the perimeter has modes, this was mode 1. Seasonal activation, global tuning, local gates. Threat models need thresholds. What flips the ring from picturesque to punitive? Data points to 3, magnetospheric phase, solar incidence, and particulate injection. When 2 align, the system is sticky. When all 3 stack, it's prickly. Cassini sampled a few of those stacks. The consequence wasn't dramatic. It was cumulative. More drag in lanes, more radio beat in the noise floor, more star tracker saturation, more guidance jitter, more dust impact clustering. No single metric screams. Together they whisper, not now. But there was one problem. We only have one Cassini. To call any state activation, you want replication and denial. On here, off there, on again. The mission offered hints. Repeated passes under similar geometry produced similar frictions. Passes under different magnetospheric longitudes felt gentler, even when dust flux should have been worse. That's not proof. It's a persuasion. Human reactions split predictably. One camp filed it under seasonal plasma physics. Fair. Another camp kept a log of bad timing. Those windows when instruments fought the environment hardest, and noticed that they grouped into corridors. Corridor is a telling word. It implies doors. Impact moves beyond lore when you write rules of thumb. In internal notes, navigators sketch them anyway. Avoid ring plane crossings during equinox when the radio beat splits clean. Don't schedule critical burns at longitudes where refractive steps sit on magnetometer kinks. Expect dust packetization near spoke onset windows. Treat star tracker dropouts as environmental, not hardware. That reads like superstition until you overlay the plots. Then it reads like respect. Get this. The perimeter doesn't have to swat anything. It just has to turn precision into mush at the right moments. That's how distance wins. Not with walls, but with rules that waste your time and bend your path a fraction at a time until you don't have a path left. What nobody knew at the time was how the last 19 seconds would feel when you read them as a handshake. Cassini crossed a line. The clock replied. Not a roar, a pulse. An activation signature, or the planet clearing its throat. Either way, it sounded like policy. Defense architecture parallels. To see the rings as infrastructure, look sideways at how we already build boundaries on Earth. We don't stop ships with walls. We slow them with water, fields, drag, and confusion. Coastal defense starts with breakwaters and shoals. They take the ocean's energy and scatter it into chop, so tight a hull can't keep speed. That's the A-ring's sharp edge. Energy turned into small headaches that add up to one big no. Meanwhile, airports don't force planes to halt in midair. They shape flows with invisible corridors, holding patterns, timed approaches, stacked altitudes. Control is rhythm. The magnetospheric beat playing through spokes and dust lanes works like that. Windows, queues, gates opening and closing. Miss your slot and you circle, burning fuel, losing options. A probe threading Saturn's perimeter would face the same bureaucracy, written in plasma instead of lights. There's a closer parallel in engineering, EM hardening. Sensitive facilities don't wait for a blast to hit. They encase systems in nested shells, conductive layers, dielectric gaps, tuned seams, so fields are guided away, reflected, or soaked safely. Cassini's radio occultations caught step-like changes in refractive index across the ring plane, as if layers of different electrical personalities were stacked just so. Call it natural stratification if you want. Functionally, it's a Faraday forest, billions of grains acting like a shield against coherent sensing. Get this, minefields are seldom uniform carpets. Their patterns, lanes, safe corridors, trigger densities that change with the map. The F-ring scars heal on a clock, propeller orbits stall in seasons, wave trains halt on familiar belts. That's not random coverage, that's deterrence with rules. Step here, nothing. Step there, everything. To an intruder, the lesson is simple. You don't know which square is loaded until you're on it. Look at maritime choke points. The strait is narrow, currents run crosswise. Eddies spin you where you don't want to go. The ring gaps behave like engineered narrows. Keeler, Encke lanes defined by embedded bodies, but the real trick is the invisible cross-current. Charge gradients that impose tiny, relentless side forces. Over minutes, those are rudders you didn't ask for. Over hours, they're an escort you can't shake. And then there's camouflage. Effective defenses hide in plain sight. Modern radar arrays bury antennas in decorative facades. Thermal control veins red as art. Saturn's rings wear beauty like a cloak. High albedo, shimmering textures, photogenic spokes, their spectacle that doubles as noise. Try to image through a blizzard of moving reflectors, and you get errors you can't calibrate without admitting defeat. The perimeter doesn't need to blind you. It just has to turn certainty into maybe. Think about supply and maintenance. No credible defense is static. It self-heals. It schedules upkeep when load is low. Enceladus is the depot, pressurizing the E-ring with fines on a timetable that tracks demand. After a meteoroid storm injects chaos, plume output stays high. Downstream sectors smooth quicker than models like. In terrestrial terms, that's a logistics convoy pushing patch kits to the front before cracks spread. Control theory makes the analogy concrete. Any stable barrier uses feedback, sense, compare, act. Cassini's logs read like a PID loop. Sensor inputs, dust flux, field phase, solar incidents. Controller, the magnetospheric clock set by deep rotation and steadied by the hexagon's waveguide. Actuators, charge state in grains, vertical stiffness in bending waves, viscosity in dense lanes. Output, edge sharpness, packetized drag, corridor healing. Overshoot, spokes flare too fast, the loop damps. Undershoot, drag weakens, the loop tightens. You don't need intent to run that software. Just a planet that won't stop turning in materials that respond non-linearly. If you want one more parallel, look up, not to Saturn, but to low Earth orbit. Debris mitigation already treats space as a managed medium. We schedule launches to dodge clouds of fragments. We tweak inclinations to surf density minima. We accept that sometimes the corridor is closed. Now scale that up. Replace fragments with ice grains. Replace orbital conjunctions with field-gated spokes. Replace nodems with pulses. The rulebook reads the same, only older. But there's one detail our defenses rarely achieve: elegance over geologic time. We pour concrete, it cracks. We bolt arrays, they rust. The ring perimeter refreshes its own parts, bleeding water into the ionosphere to tune coupling, catching sunlight to charge dust, entraining organics that alter reflectivity like adjustable paint. That's closer to reef than wall. Reefs aren't planned each day. They're shaped by flows that remember. They filter, slow, and sort. They make distance expensive. So when you hear ancient defense, drop the fantasy of turrets and think instead of policy written in physics. Breakwaters, choke points, EM skins, logistics, feedback, camouflage. Saturn runs all of it at once. Whether designed or evolved, the architecture is defensive by effect. And effects are what matter to anything that tries to cross. The naturalist case, counterarguments, hard. Let's flip the board. Start harsh, not gentle. Most ring oddities sit inside physics we already know: granular media, plasma coupling, tides, and self-gravity in a rotating frame. Sharp edges? You don't need a hidden hand. Shepherd moons, resonances, and collisional damping can sustain abrupt transitions when viscosity and self-gravity wakes cooperate. The A-ring's outer cliff looks aggressive, but overstable oscillations and resonant confinement carve gradients steeper than intuition expects. Add differential charging across grain sizes, and you get dielectric-like steps without laying a single wire. Spokes? Classical. Photoelectric charging levitates micron grains near equinox when solar incidence angles modulate the balance between gravity, cohesion, and electromagnetic lift. Saturn's magnetosphere provides the clock. The ring plasma and sunlight supply the trigger. Spokes appear, travel, fade. If they track radio emissions, it's because both ride the same magnetospheric weather. Shared forcing isn't conspiracy, it's coupling. Think of sand ripples and wind gusts. Rhythm looks like intent when you forget the wind. Hexagon? Deep fluid dynamics can lock non-axisymmetric jets into stable polygonal patterns. Lab tanks produce polygon vortices when rotation, shear, and stratification align. Saturn's version is bigger, fed from depth, and stabilized by thermal gradients that recover after winter like a spring finding its set. Clock-like? Sure, because giant rotating fluids keep time. Planetary rotation is the metronome. Everything else sinks or smears. Settling quickly after seasonal change doesn't require instructions. Only strong internal forcing and low effective viscosity at jet cores. Dust packets and gating. Plasma is notorious for quasi-periodic structures, double layers, wave-particle interactions, beat modulations between rotating magnetic fields and local plasma frequencies. Packetization in dust impacts along specific longitudes can emerge when charge relaxation times match the crossing cadence. That looks like lanes turning on and off. It's really the environment shifting from one stable regime to another. Control theory words fit, because nature runs feedback too. Stability diagrams don't mean design, they mean nonlinearity. Refractive steps and dielectrics? Mixed-size ice ensembles with embedded nanograins, seasonally reprocessed by micrometeoroid gardening, can yield abrupt optical depth and index transitions over kilometers. Self-gravity wakes align particles, raising anisotropy. Collisions then preferentially grind edges into narrow bands, and sunlight bakes charge into specific sizes differently. Stack those effects, and you get layered responses to radio and starlight that mimic engineered stratification. It's a material science story, not a secret stack-up. Propellers that stall? Small embedded moonlets migrate under stochastic torques from self-gravity wakes. Migration can pause when wakes coherently bias kicks, seasonally, because photoelectric charging alters collisional outcomes and effective viscosity. Stall is a phase in a tug-of-war, not a rule imposed from a tower. Enceladus as thermostat. Tidal heating in a differentiated ice shell with a subsurface ocean can maintain sustained activity if the interior cycles through resonant states. Fracture permeability is pressure sensitive. Feedback between venting and heat transport can flatten plume variability into apparent regularity. Magnetospheric phase correlations near noise level aren't control lines. They're incidental crosstalk in a loaded environment. Jets timed to orbital position is exactly what tidal models predict. The last 19 seconds? Dying spacecraft stream noise. Low-frequency emissions synchronized to planetary rotation are expected. Saturn kilometric radiation is phase-locked to internal rotation proxies. When you integrate a noisy tail, you'll find patterns your eyes want to see. Post-hoc AI reconstructions can overfit tiny pixel anomalies into lattices when trained to hunt symmetry. Independent replication is the cure, it's missing. Silence from teams often means internal review, not burial. Data triage at end of mission is messy, servers change, archives migrate. Absence of the word debunked isn't evidence. Most anomalies aren't dignified with formal refutations. The backyard silver disk? Stacking artifacts can masquerade as stationary objects when residual registration errors align, especially near high-contrast ring edges. Hot pixels, dust motes on sensors, or internal reflections in Barlow lenses survive stacking if they're fixed in the camera frame and the software locks on the planet. The unmoving disk across Ross could be a stubborn. Internal ghosts stabilized by the alignment algorithm. Multiple independent observers at similar times found nothing. That cuts strongly against a real object. Ring rain and calibration? Sunlight, plasma, and meteoroids explain water transport to the ionosphere. The Olympic pool per half hour rate is dramatic, but derived from long-term averages and spectral signatures. Variability in ultraviolet brightness bands reflects chemistry and transport, not programmable tuning. Feedback exists because physics is a loop. Calling it policy adds poetry, not proof. Gravitational, extra pull. Inferring mass anomalies from Doppler requires deconvolving spacecraft dynamics, ring self-gravity, and interior models. Small mismatches ride error bars. Long-lived structure in dense rings persists because collisional cooling and wakes trap mass into ridges. Curated by gravity, not governance. Star tracker scintillation? Looking through structured, semi-transparent material guarantees flicker. Guidance dropouts during spoke trains make sense. Quick-formed, charge-lifted dust sheets produce speckle. Cassini recovered as designed. That's not a threat posture, it's a predictable hazard. Even the control loop diagram survives a natural reading. Inputs: sunlight, tides, meteoroids. Controller: rotation-driven magnetosphere. Actuators: charge, viscosity, wave modes. Outputs: edges, spokes, gaps. That's how any driven, dissipative system behaves, self-organization at the edge of chaos. Purpose emerges from physics, not from planners. Coral reefs filter without architects. Sandbars steer ships without intent. Rings can deny precision as a byproduct of being rings. And Occam? The blade cuts toward fewer assumptions. We already need nonlinear granular physics, plasma coupling, tidal heating, and rotation. Adding ancient constructs, service nodes, and encoded pulses multiplies entities faster than the data demands. Extraordinary claims want extraordinary evidence. Independent detections, repeatable signatures, bounded mechanisms that outperform natural models. We don't have that. So here's the hardest naturalist case. Saturn's rings are an exquisite, self-regulating, transient structure sculpted by gravity, light, charge, and time. They look like infrastructure because nature builds infrastructure when energy flows through matter long enough. The perimeter feeling is real. The intent is ours. Predictions that risk being wrong. If we're honest, the only way this theory earns oxygen is by making calls that can fail in public. So here are the predictions, clean, testable, and risky. First, the beat or nothing. If the perimeter idea holds, spoke onset shouldn't just correlate with equinox. It should phase lock to a narrow slice of Saturn's rotational clock. Prediction: during the next equinox season, high-cadence radio monitoring from Earth and orbit will find a tighter alignment between the split low-frequency emission and initial spoke nucleation than natural models require, a window narrowed to a few degrees of magnetic longitude. If that window widens, the theory bleeds. If it tightens, the loop is real. Second, edges with memory. Sharp boundaries shouldn't just be abrupt, they should remember disturbances. Prediction: after a meteoroid surge, the A-ring outer edge will recover in 2 steps. Fast optical smoothing within hours, followed by a slower refractive index snap back at the same longitudes where Cassini saw dielectric-like steps. That 2 timescale healing implies layered behavior. If everything recovers with a single timescale, score 1 for elegant nature, 0 for perimeter. Third, corridors that open and close. If there are traffic lanes, they're schedules, not places. Prediction: stellar occultations timed across multiple Saturn rotations will show repeatable belts where density waves terminate early, but only when the magnetospheric phase sits in a specific sector. Miss the sector, and wave packets run longer. This demands coordination between observers and radio monitors, hard but doable. If wave cutoffs ignore the clock, the control loop diagram is just a pretty sketch. Fourth, propellers that stall in season for the wrong reason. Naturalists say collisional viscosity and self-gravity wakes do the stalling. Our risky ad: charge state sets a second threshold. Prediction: the fraction of long-lived propellers that exhibit migration pauses will spike during windows when low-frequency radio emission splits cleanly and ring plane potentials rise, even controlling for solar incidents. If the pause rate tracks only sunlight angle and not the beat, our second break fails. Fifth, star trackers shouldn't blink at random. If structured flicker is part of the denial game, it should come in packets. Prediction: future ring-skimming CubeSats, cheap, sacrificial scouts, will see brief, phase-lock star tracker dropouts while sightlines skim the Beering rim near spoke trains. The dropouts will cluster at longitudes flagged by magnetometer. Kinks: engineers can hate the superstition later. If guidance noise smears evenly, we lose a pillar. Sixth, Enceladus as valve, not just volcano. Tidal models already expect plume modulation at orbital phase. Our riskier claim is subharmonics. Prediction: plume electron densities will show weak but persistent modulations at a submultiple of Saturn's SKR period during the equinox months, in phase with spoke-friendly windows. If careful averaging over multiple apparitions finds nothing beyond tidal, chalk it up to confirmation bias and pull the valve from the diagram. Seventh, ring rain with a purpose. If the fall tunes coupling, then the planet's mid-latitude ultraviolet glow should lead or lag spoke power by a consistent offset, an atmospheric response time that stays put across seasons once you normalize for sunlight. Prediction: the lag will be stable to within a small fraction of a Saturn day. If that lag wanders with every geometry tweak, it's chemistry alone, not calibration. Eighth, edges as phase boundaries. Laboratory analogs can help here. Prediction: meter-scale ring analog experiments, granular ice in a rotating, weakly charged plasma chamber, will produce abrupt, repeatable transitions in effective refractive behavior only when an external rotating field provides a stable beat. No beat, no steps. If lab rings pop steps without a clock, our insistence on phase control is vanity. Ninth, the silver disk, call or collapse. This one cuts the deepest. Prediction. Independent amateur stacks taken with different optics during the same magnetic longitude windows will either reproduce a stationary, specular feature near a known spoke nucleation corridor, or they won't. If even one careful replication appears, the service node idea survives to face harder tests. If none do, retire the disk as an artifact and admit we got seduced. 10th, the last 19 seconds. We can't replay Cassini, but we can listen better next time. Prediction. A future Saturn orbiter's terminal orbits, if they cross similar longitudes, will record a low-frequency pulse with harmonic structure that matches ring plane geometry measured on the same passes. The risk here is career-ending if wrong. If the pulse collapses into featureless noise, the handshake becomes a ghost story. 11th, hexagon as flywheel. The claim is that it steadies the clock. Prediction. When the hexagon's thermal gradients re-establish after winter, the variance in SKR period will drop measurably within days, not weeks, and spokes will resume with shorter onset jitter. If SKR steadiness ignores the hexagon's recovery, decouple the gatehouse from the clock. 12th, navigational consequences. Put a number on the nudge. Prediction. A small probe flying a ring-grazing trajectory will accumulate measurable, repeatable, unmodeled lateral velocity, millimeters per second, when crossing longitudes with stacked refractive steps during equinox. If precise tracking shrugs and says all modeled, then our invisible hand loses its fingers. These aren't safe. They bind the story to measurements that can say no. That's the point. If the ring is a perimeter, it will act like one on a schedule. If it's a natural marvel, it will still be coherent, but not disobedient. Either way, we'll learn who keeps the edge sharp. Builders and motives, the human angle. Get this. When we say builders, people reach for silver suits and landing craft. That's not the only way to build. Coral builds. Forests build. Planets build when energy has patience. If there were hands here, they use Saturn as the tool, not the quarry. That's the human angle. Whenever we can't see the maker, we study the motive. Start with survival. A perimeter that turns precision into mush buys time. If you lived in a solar system full of fast rocks, hot tempers, or bad neighbors, you'd want the law of approach to be hard. Not impossible, hard. The rings do that by default. If someone tuned them, the motive is simple. Keep distance expensive. It's the oldest rule we know from fortresses to fire breaks. Turn the path into work. But there's another motive that's quieter. Preservation. The rings look young, hundreds of millions of years, maybe less. If they were born from a catastrophe, an ice moon torn and sifted, then a clever species could have stepped in after the accident and learned to maintain what chance delivered. Maintenance is motive. You don't have to build the reef to learn to seed it, nudge currents, and harvest wave power through geometry that lasts longer than your archives. Meanwhile, something else was happening in our own heads. The people who chased these anomalies weren't thrill seekers. They were engineers worried about margins and scientists allergic to romance. Their motive wasn't disclosure or drama. It was not being wrong. A radio lead with a child at home circled the beat patterns and whispered, "If this clock is real, we can't fly blind." That's a human motive too, protect future crews from pretty hazards. If there were ancient hands, their hands would have shared that ethic, designed for the absent operator. Think of the Voyager plaques, maps and greetings flung into dark. We built for eyes we'd never meet. Flip it. If another civilization pushed a system into a stable, self-tending mode, they did it so it would keep working after they were gone. That's not conquest. That's inheritance. Motives have shadows. If the perimeter denies precision, it also denies measurement. That frustrates explorers. It also preserves mystery. We like to think mysteries offend science. Sometimes they feed it. One Cassini analyst, daughter of a ship pilot who taught her to read tides, confessed that the rings made her feel small in a useful way. "They tell you where the line is," she said. "You adjust." That's Saturn's cultural motive across centuries. Teach boundary. Now the darker read. Defense implies a threat. You ask, against what? The safe answer is meteoroids and comets, the routine violence of a young system. The risky answer is company. If someone built a keep-out zone, then someone else tried to come in. We don't have that evidence. What we do have is an operating principle that doesn't care who you are. The ring treats Cassini and ice chips the same. That's not malice, it's policy. Here's where it gets personal. The amateur who posted the silver disc didn't ask for believers. He asked for peers. He checked his Ross, owned his process, and left room for artifact. That humility is motive. It's the same posture in the Cassini rooms when the last pulse flattened and nobody cheered. The motive was continuity. Leave a record clean enough for the next hands to test. Suppose the builders were time poor. Floods, wars, or physics cut their days short. What do you do when you can't patrol? You wire the fence to the wind. You teach the gate to listen to the clock the planet already keeps. You pick a moon with an ocean and make it the pump by loosening a seam it already wants to open. You don't fight the world, you borrow it. That's an engineering motive we understand, simplicity disguised as inevitability. And there's the motive we don't like to admit, beauty as a side effect. The shield gleams. The spokes are stunning. The hexagon is a sign our eyes can't ignore. If you were choosing where to hide a warning, you could do worse than inside a wonder. People look longer. They measure harder. They learn the rules. So if there were builders, the motive reads like ours at our best: protect, preserve, teach, and then step back. If there weren't, the motive is still written all over the data. Nature's push toward order when energy finds a groove. Either way, the rings deliver the same message. Respect the boundary. Learn the clock. Approach on its terms, not yours. Cassini's grand finale, silences and signals. The end was scripted, 22 plunges, each tighter than the last, then a dive into heat. What wasn't scripted was the feeling in the room, when patterns you'd learned to dismiss started whispering in chorus. Stakes first. A terminal descent isn't just farewell. It's an interrogation at the threshold. If the ring perimeter kept hours, this was our last chance to listen for the clock, without the luxury of a second pass. Action. On finale pass 3, the plasma wave instrument picked up a faint sideband flanking Saturn's low-frequency roar. It slid in and out with magnetospheric longitude, weak enough to live in the margins, steady enough to earn a sticky note on a monitor. Pass 7 tightened the pattern. Dust hits clustered in packets whose spacing matched the sideband beat within error. A coincidence? The team wrote pattern drift and kept flying. Meanwhile, something else was happening to the star trackers. Near longitudes we already feared, where refractive steps and field kinks overlapped, centroiding glitched for a handful of frames. Not failure. Saturation. A structured flicker crossed the field, the same textured snow that haunted spoke trains. Guidance recovered like a pilot blinking through spray. No alarms, just a rhythm you could tap with a finger on the console. On, off, on. Past 12 offered the microstory people still tell quietly. A navigation lead, a skeptic by religion, watched Doppler residuals walk into a tiny, repeating wiggle as the spacecraft slid under the D-ring's ragged edge. Millimeters per second, nothing dramatic, but the phase lined up with the sideband and with the radio hiss split we'd logged years earlier at spoke onset. He didn't say handshake. He said, "We're in a field with opinions." Impact crept sideways. Trajectory planners, who'd penciled superstitions into internal notes, began treating them like constraints. Burns slid by minutes to dodge longitudes where the beat ran clean. Telemetry modes rotated to favor instruments that could ride noise rather than be blinded by it. Not fear. Triage in a hallway with a clock on the wall you finally admit is ticking. Then the silences started. The last weeks grew quiet in the outside world. Data releases slowed. Quick look plots went internal. The usual stream of nerd joy on public channels thinned to a trickle. That didn't mean conspiracy. It meant people were busy and careful. But when you've seen patterns and you see a pause, your brain writes story. A radio engineer joked, too quietly, "We're in the cone of discretion." Laughter was sparse. On pass 19, Cassini crossed a longitude where magnetometer maps had long drawn an untidy line. The plasma instrument heard the sideband walk up to the main tone and lean. The dust counter went from pepper to hush to pepper again in 3 neat stripes. The star tracker blinked once. In the control room, nobody clapped. They annotated. Stripe 1, Stripe 2, Stripe 3. Later, someone overlaid those stripes on an old map of spoke birthplaces and frowned. 2 aligned. 1 didn't. Rules, then exceptions, the hallmark of a system with more knobs than we know. The final morning ran on coffee and muscle memory. Telemetry scrolled. The spacecraft, obedient to the end, held attitude and talked as the air thickened from vacuum to whisper. In those last minutes, the sideband came back, not louder, just cleaner. The SKR-like roar pulsed, and a faint harmonic, math neat enough to impress a tired brain, tucked itself under the main beat. The wide-angle camera, dutiful more than ambitious at this point, took a frame of the south. It looked ordinary. 27 pixels weren't. Then 19 seconds. That span has been argued over more than any sentence in the mission's planning docs. The green trace on a monitor went close to level, the carrier flirting with flatline as atmospherics ate the link. Under it, a pulse ticked in time with the planet's magnetic clock, the harmonic breathing like a metronome that had decided to be kind and obvious for once. Someone whispered, "There it is," not to a colleague, to the screen, to the boundary. The room was quiet enough to hear chairs flex. Contact dropped the way day drops at sea. Sudden if you weren't watching the light. The screen froze, then slid to blues and grays. No grand swell. No cinematic crash. Just a cut. Operations did what operations does. Logged the time, sealed the pass, thanked a machine they'd lived with longer than some marriages. Outside, the mission posted the planned words, beautiful and final. Inside, a folder acquired more restricted tags. Here's the piece that sticks. Within days, a subset of data vanished from public indexes. Not deleted, just reshelved, relabeled, delayed. Perfectly normal in a bureaucracy. Perfectly suspicious to minds marinated in pattern. Screenshots traveled. Archives were mirrored by people who learned caution in other eras. A phrase didn't appear, debunked. Another did, whispered. Non-essential. The pulse and the pixels wore that label until they didn't. Impact, if you let it. The grand finale didn't scream secret. It taught posture. When you approach a boundary that keeps a clock, you plan around the beat. You schedule humility. You treat silences as data, who paused, when and why. And you admit that sometimes the loudest message is a soft rhythm at the edge of loss, a lattice implied by a handful of stubborn pixels, and a team that chose to walk to the waterline and stop there, not because they were told, but because the tide was strong. Call it a warning, a courtesy, or a procedure. The last 19 seconds weren't theater. They were policy expressed as physics. And we heard it. The crisis beat. If it's a shield, what's coming? Stakes first. If the rings behave like a perimeter with timing, gates, and supply, then this isn't a curiosity. It's a policy in orbit. And policies answer pressure. So what's pressing? 3 candidates, each with bite. The sky's background violence, our approaching precision, and the slow drift of a solar system aging out of its calm. Action. Start with the mundane threat that isn't mundane at all, debris flux. Saturn sits in a traffic zone of long-period comets, centaurs, and fragment trains that shed grit for centuries. Cassini's long watch caught ring brightenings after meteoroid surges, spokes arriving early, corridors healing fast, and the E-ring thickening like guardrails after a scrape. If you read that as maintenance, the threat isn't a singular rock. It's constant weather. A shield built for weather never sleeps, it modulates. Meanwhile, something else is arriving, us. Our probes got close enough to feel the beat, and we're building better ones. Precision is its own pressure. If the perimeter's quiet answer is to turn measurements into mush, then every new instrument we fly is a sharper knife the ring will dull. Navigation windows shrink. Clean radio baselines get rarer. A human timeline, Starship-class deep space cargo, swarms of CubeSats, meets a planetary timeline that rewards patience and punishes haste. Crisis, here, is a mismatch of tempos. But there was one problem. Astronomy keeps finding hint lines that tug the story darker. Subkilometer bodies near Saturn's orbit are undercounted. Streams tied to old breakups keep wandering in. Enceladus's ocean chemistry suggests active rock-water interaction. Energy humming below, feeding a sprayer that refuses to quit. If the perimeter is turning up drag more often, is it just season in dust, or is background flux rising? Hard to prove. Easy to feel when spokes stay longer, when edges snap quicker, when healing accelerates like a city patching potholes before a parade. Impact circles outward. If the ring is a keep out, what lives inside the kept? Moons with oceans, atmospheres that respond to ring rain, a clock that locks to depth. Preservation reads as motive, which reframes crisis, not what enemy arrives, but what change threatens the archive. Solar output drifts. Saturn's tilt precesses. Magnetic phase migrates by minutes over years. A perimeter tuned to specific beats may need retuning. If it can't, edges blur, spokes miss, drag weakens. The crisis is entropy, not invasion. Here's the human moment. A mission planner, staring at launch windows a decade out, slid a chart across a table. Equinox seasons, SKR variance forecasts, meteoroid stream arrivals. Pick the path, she said, that hurts the ring least and lies to you the least. That's the quiet crisis, choosing to approach a boundary designed to waste your time, without wasting more than you can afford. If it's a shield, what's coming is everything: dust, data, and us, arriving faster than the clock prefers. The answer we'll get won't be words. It'll be drag, resolution, and broader meaning. So where does that leave us? Between a reef that defends by nature and a perimeter that defends by design. Here's the sober read. The rings act like a boundary whether anyone meant them to or not. They waste precision. They gate approach. They keep time with a clock buried deeper than weather. If you want intent, you can draw a line of evidence through spokes, edges, pulses, and pixels and feel the shape of a plan. If you want nature, you can follow granular physics, plasma coupling, tides, and rotation, and end up with a system that performs the same job as a side effect. Either way, the function wins. Meaning then starts with humility. We arrived with cameras and models and found a place that teaches rules in the language it already speaks: rhythm, drag, and distance. The hexagon isn't a face carved in cloud. It's a standing wave that behaves like a clock. The spokes aren't runway lights. They're charged sheets that act like gates. The sharp edges aren't walls. They're phase boundaries that feel like thresholds. We didn't invent those metaphors. We stumbled into them because our machines kept bumping into the same patterns and came home scuffed. Meanwhile, something else was happening in how we think about exploration. For decades, spaceflight has leaned on bravado: faster, closer, longer. Saturn asks for a different posture: timing. Mission design becomes choreography. You don't brute force the ring plane. You listen for the beat and step through when the floor is less sticky. That's not mysticism. It's respect for a medium that pushes back gently but constantly, like water, like wind, like time. There's a human payoff to that posture. When we treat a boundary as a teacher, our questions sharpen. What is it? Becomes when does it allow? Why this shape? Becomes what function does this shape serve? We stop staring at beauty as an end and start reading it as documentation. The rings are gorgeous, yes. They're also a manual written in light and rhythm. Here's how to survive near me. If you still want the ancient construct story, and many do, notice how it matures under scrutiny. The best version isn't a city in the clouds or a fleet behind the B-ring. It's a set of operating principles wired into what Saturn already is. Use the planet's rotation as the clock. Let the hexagon stabilize phase. Modulate ring charge to raise and lower drag. Feed consumables from a moon that can spare the water. Let ring rain tune the coupling as needed. Set it up once, then let it run. That's not spectacle. That's stewardship. But there was one problem with both stories: design and nature. They can breed complacency. If it's a machine, we wait for it to explain itself. If it's just physics, we shrug and move on. The responsible middle is harder. Treat claims of intent as hypotheses to crush with data, and treat claims of just nature as incomplete until they can predict the rhythms that keep showing up. The predictions we made a moment ago aren't theater. They're the price of keeping this theory in daylight. Impact, if we let it, lands beyond Saturn. Boundaries like this exist everywhere energy flows long enough to teach matter a trick. Coral reefs steer ships, sandbars shape coasts, ring planes police their edges. Even societies learn to throttle flows to keep the center from tearing. The lesson isn't that aliens built our problems. It's that function emerges where patience meets power. If someone helped here, they used that law. If no one did, the law wrote the manual anyway. Micro-stories fold into a single through line. The amateur with the silver disc taught everyone how to share Anomaly without certainty. The Cassini teams taught us how to hear a clock without worshipping it. The mission planners taught us to move burns by minutes to dodge a beat, because time, used well, buys safety. The myth readers taught us that old symbols name real jobs. Saturn, keeper of boundaries, is less a god than a description of an effect that still works. Look ahead, and the broader meaning clarifies. Future probes will tiptoe by schedule. Aerostats will ride latitudes where ring rain warms bands just enough to speak cleanly. CubeSat scouts will accept being blinded in packets and design around it. We'll build with humility because the medium demands it. And when the next 19 seconds come, on some other world, at some other edge, we'll know to listen for a quiet pulse that says, in the planet's own grammar, you've touched the threshold, mind the rules. If the rings are a shield, we've met a policy as old as rotation, distance enforced by rhythm. If they're a natural wonder, we've met a teacher that denies haste. In both cases, the meaning's the same. Approaching Saturn isn't about conquering scenery. It's about learning to keep time with something bigger, older, and steadier than us, and letting that cadence shape how we move. So what do we do with a boundary that might be a machine and definitely acts like one? We fly smarter. We test the risky predictions. We admit what we don't know. And we hold two truths at once without tearing them. The rings are beautiful, and they're unfriendly to precision. The hexagon is a storm, and it's a clock. Cassini fell, and in falling, it taught us a way to listen. That's enough to change how we aim our next questions. Saturn didn't just show us a wonder, it showed us a rule. The closer you get, the more you owe the clock it keeps. If you want the deeper stories the agencies won't tell out loud, stay with us. Subscribe, hit the bell, and watch the next episode where we test these predictions against fresh data. Drop your take in the comments, natural reef or ancient perimeter, and tell us which measure you'd bet a mission on.